All right, welcome back to class 21. Here's another laminar pipe drop calculation where we have a 100 millimeter inside diameter pipe. It's carrying 0.5 cubic meters per hour of ethyl alcohol through 10 meters of pipe. We want to know what the Reynolds number is, whether it's laminar or turbulent, and what's the friction factor, and what's the pressure drop, and what is the head loss. Okay, so we changed it up just ever so slightly to trying to get back to that idea of head is a important concept and way to treat, not concept, but an important way to treat pressure drop calculations. So as I did in the previous one, let's start by changing this cubic meters per hour into a, it's supposed to be 0.5, into per second. So we're going to divide by 3,600 seconds per hour and get up with 1.389 E minus 4 cubic meters per second. And then we could find the velocity by dividing that flow rate by the inside area. So 1.389 E minus 4 divided by pi over 4, and we have 100 millimeters, so that's 0.1 squared. So we end up with 1.768 E minus 2 meters per second. The Reynolds number, it's easier to go velocity times diameter times kinematic viscosity. So we have the velocity of 1.768 E minus 2 meters per second. Keep the units in there. And the diameter is 0.1 meters. So we'll divide. This is ethyl alcohol. So let's see, ethyl alcohol, we have that. And its kinematic viscosity is going to be 1.51 E minus 6, and these are meters squared per second. So that's 1.51 E minus 6 meters squared per second. You can see meters, second. Oh, they cancel out. And we get 1,171, which is less than the 2,100, and therefore it's laminar. So we've answered 2 questions so far. Reynolds number and laminar or turbulent, yay. The next thing we want to do is find a Darcy friction factor for laminar flow is 64 divided by Reynolds number. 64 divided by 1,171 is 0.0458. And it wouldn't kill us to take a look and see. In the previous one, example, we couldn't even find it on the Moody diagram. But in this case, we anticipate it to be 0.05. 0.05 is right here. So right here is 1,000. So right here is 2,000 right here, right? So that's one. This is 1,000. This is 2,000. You could think of that's probably 1,500, like right in there. So maybe we're somewhere like right in there. And yeah, I guess I could believe that, right? Somewhere like somewhere right in there. Okay, so I didn't draw that perfectly right, but somewhere in that region, right there, somewhere in that zone. Just a kind of a confirmation that we're in the right location. So here's the Darcy friction factor. And I just like the name Darcy. Here's our delta P. It's going to be the coefficient of friction, not the coefficient of friction, the Darcy friction factor. I like saying it again. There, I said it again. And then rho V squared over 2. So 0.05458. The length, they wanted 10 meters of pipe. and divide it by the diameter of 0.1. And then the density of ethyl alcohol is 789 kilograms per cubic meter. Did I stop what I used? Sure enough, 789. And the velocity 1.768 e minus 2 squared divided by 2. And what do we end up getting? It's probably going to be a small, and it's not too bad. 0.6730. And these are newtons per meter squared because we used base units of newtons and meters all the way through. So we don't necessarily, that's the same thing as a PA, as a Pascal, right? It's so small, that's fine. Just keep it that way. And there's the Pascal right there. So there, pressure. And then they also wanted head loss, right? So what is the head loss? Remember that H, and this is going to be the pressure drop, so that is head loss. We'll take delta P and divide it by gamma. Or you can take rho and the density there, so you could use that. But let's just keep it 0.6730 divided by, and ethyl alcohol has a specific weight of 7.74 kilonewtons per cubic meter. So you got to be careful of that kilonewtons. So we need to put that in there as 7,740 newtons. And we get 8.676 e minus 5 meters. That's way too small to do in meters, so you would probably want to report that in millimeters. It's still kind of small, but don't have so many trailing zeros to have to worry about. So you go. So there's the answer. And there's another video, and there's another example, but we don't really need it. It's sort of an unnecessary example because the other one was good enough. But